Okay, hello everyone. This talk focuses on multi-objective query optimization. You all know classical query optimization, which was introduced in the end of the 70s. And from today's perspective, one could say that people had relatively few choices when it comes to data processing at that time. And in that context, it was perfectly appropriate to compare alternative query plans based on only one cost metric, which is execution time. And then the goal of query optimization was to find a plan with minimal execution time. Nowadays, people have many more choices when it comes to data processing. We can use cloud computing, crowdsourcing, approximate processing techniques, for instance. And many of those provisioning options and processing techniques, they actually motivate people to consider multiple cost and quality metrics according to which to compare query plans. For instance, when using cloud computing, then users typically care not only about execution time, but also about monetary execution fees. And sometimes it's possible to trade between them by adapting the type and number of resources you rent from the cloud provider. Or from the provider's perspective, it might be interesting to consider trade-offs between the amount of system resources dedicated to one user and the performance perceived by that user. And now you add approximate processing in the mix, then you also care about result precision. So in general, in many scenarios nowadays, you want to compare query plans according to multiple execution cost metrics. So query plans are associated with cost vectors instead of cost values, and that leads to multi-objective query optimization, where the goal is to find a set of query plans realizing optimal execution cost trade-offs, also called the Pareto frontier. Classical query optimization is already an NP-hard problem. So you can roughly divide corresponding algorithms into two groups. First of all, exhaustive algorithms that formally guarantee to generate optimal plans but have exponential complexity, and heuristic algorithms that do not guarantee to generate optimal plans, but they have polynomial complexity and can be applied to much larger queries. Now, for classical query optimization, you have both types of algorithms. For multi-objective query optimization, however, so far you only had exponential complexity algorithms. So in this paper, we propose the first algorithm for multi-objective query optimization that has polynomial time, and it is generic enough to be applied to all the scenarios that I have outlined before and to many more. In the following, I'm going to give you a quick high-level overview of that algorithm. First of all, I guess most of you know the dynamic programming algorithm for query optimization, for classical query optimization. I'm quickly going to illustrate it here. It decomposes a query into its subqueries, and then it starts by generating all plans for the smallest subqueries. It compares their execution time in classical query optimization to identify optimal plans for each subquery. It discards the other ones, and then it uses those optimal plans in order to generate plans for the larger queries. It discards the other one until it finds an optimal plan for the entire query. Now, the generalization of that to multiple execution cost metrics is quite natural. If we have, for instance, monetary execution fees and execution time, then we just keep the Pareto frontier, the set of Pareto-optimal query plans for each of the subqueries instead of only one optimal plan. The problem with that approach is that you might have way too many Pareto-optimal plans for a subquery, so optimization can become terribly slow. We can, however, solve that problem by basically introducing a grid in the cost space, and now we say that we keep at most one query plan for each of those grid cells. And if we do it in the right way, then we can be sure that the number of plans that we need to keep for each subquery is upper bounded by a polynomial in the input query size as measured by the number of tables that we join. And at the same time, we can be sure that our approximation of the true Pareto frontier is within a bounded distance of the real Pareto frontier. This approach works for small and perhaps medium-sized queries. The problem is, if you have larger queries, as the number of subqueries grows exponentially in the query size, you just have too many subqueries. The following algorithm is based on the hypothesis that even though you might have many subqueries, you actually only need a small subset of them in order to get a good approximation of the Pareto frontier for the entire query. So we basically assume that most subqueries are actually not interesting because they correspond to intermediate results that you never want to generate. Now the only problem is, of course, okay, if you assume that is a small set of subqueries that is sufficient if we work with them, how do we identify those subqueries, those interesting subqueries? A subquery is interesting because it appears as part of a Pareto-optimal query plan, but originally, of course, we do not know the Pareto-optimal query plans. However, what we are going to do in the following, we are going to sample plans that have a relatively high probability of being Pareto-optimal or close to it. So, I start with a random query plan, then I apply local mutations in order to obtain a set of neighbor plans. I compare the cost of those neighbor plans against the cost of the current plan. And if I find a neighbor plan whose cost is lower according to all cost metrics at the same time than the current plan, then I make this neighbor plan the new current plan. And I repeat that, I execute local search until finally I come to a plan which is a local Pareto optimum, meaning that none of the neighbors has better cost according to all metrics. Now I have a local Pareto optimum. I extract the subqueries that appear as part of that locally optimal plan. Now I approximate the Pareto frontiers only for those subqueries. I can repeat the whole process. I start with a new random query plan, then I use local search in order to get to a local Pareto optimum, and finally I extract the subqueries, which might now include new subqueries compared to the previous iteration, so I also approximate the Pareto frontier for them. And if I keep doing this with hundreds or thousands of iterations per second of optimization time, then the hope is that I will get to a fairly good approximation of the true Pareto frontier for the entire query long before we have explored a significant fraction of the total number of subqueries. So, of course, it is a very high-level overview of our algorithm. You find more details in the paper about how we efficiently merge the results from different iterations, how we refine approximation, resolution over time, and we also propose a couple of improvements that very significantly speed up the local search phase. For instance, we execute multiple mutations in different parts of the query plan at the same time and thereby skip some steps on the way from a random plan to the next Pareto optimum. And we analyze mutations before we apply them in order to conclude that certain mutations can never lead to improvements in a given situation. Coming to the complexity analysis on a high level, of course, we can show that the number of query plans that we keep per subquery is a polynomial in the input query size. Also, the number of subqueries that we touch per iteration is bounded by a polynomial. In the same way, the complexity of one step of local search is polynomial, but in order to say something about the complexity of local search as a whole, we also must say something about the expected distance between a random plan and the next Pareto optimum. And in the paper, we develop a statistical model that gives you an expected path length from a random plan to the next local optimum for a given number of query tables and for a given number of cost metrics. And we also verify the predictions of that model by additional experiments that you find in the paper and make sure that the predictions match reality quite well. So the expected number of steps is also a polynomial, and therefore the complexity of one iteration is a polynomial. In the experimental evaluation, we compare our algorithm against 7 competitors in terms of how quickly they converge to the true Pareto frontier. So we report approximation error as a function of optimization time, and we experiment with different number of tables that we join and with different numbers of metrics that we consider. Here you see results for randomly generated queries with star-shaped join graphs and equality joins, and for the cost metrics execution time, result precision, and buffer space consumption. But we consider many more scenarios in the paper and report corresponding experimental results, which are always quite similar to what you see here. So we compare against general purpose algorithms for multi-objective optimizations, like genetic algorithms. We also compare against generalizations of classical randomized query optimization algorithms and against exponential time approximation schemes for multi-objective query optimization, which are drawn in green in this figure. And as you see, the only scenario in which you want to use those exponential time approximation schemes is for low number of metrics and low number of tables. For the other cases, you see the error of our own algorithm drawn in red. You see that our algorithm often significantly outperforms all other baselines, often by several orders of magnitude. So probably you want to use this algorithm for the other cases. So in summary, we propose the first polynomial time algorithm for multi-objective query optimization. It treats significantly larger queries than exponential time approximation schemes, and it outperforms all baselines significantly in terms of the approximation error. Thank you very much for your attention, and now look forward to your questions.
This is very interesting research.
Thank you.
I was wondering, because before you showed the experimental comparison, I was talking about genetic programming. But I guess that your genetic experiment is running the genetic algorithm from beginning to end, right? I'm wondering that if you can adopt the genetic programming just for your first part, which is randomization part, because when I see that picture, it immediately occurred to me it's very similar to genetic programming. So you can take the genetic programming as your starting point, and then your algorithm of the frontier construction can kick in.
So you basically propose to use a genetic algorithm instead of the local search for the first part of the algorithm to identify interest.
Because that's kind of natural to the genetic program.
Yes, I mean, genetic algorithms have been very successful for query optimization, but you see that we compare against the genetic algorithm in our experiments, which performs not as good as our algorithm. So when it comes to replacing the first phase of the algorithm by this one, I haven't tried it out. I would expect that local search might be better suited because we need a high number of iterations. So genetic algorithms, they have a little bit higher overhead because you have to generate a whole population of plants, of course. So for the first part of the algorithm, I would ideally want something which gets me only one good plan very fast, such that I can do like hundreds or thousands of iterations per second. And with a genetic algorithm, I'm not sure whether I would get the same speed.
Yeah, as I see it, you kind of do it one at a time, but genetic programming kind of like a batch processing of the idea. You actually get a whole lot of random plans at the same time. Yeah.
So you would propose to use a whole batch?
Just kind of a try it out. I don't know. I might try it. Just use the genetic programming for the first part to get your random sample.
Yes, I mean, in principle, you could use many randomized algorithms for the first part. I mean, local search seemed like the lowest overhead variant to me. This is why I went for it. Also, we have actually some nice additions to standard local search, which make it particularly efficient. So with those additions, I would guess that a local search actually is better suited, but I haven't tried out different randomized algorithms for the first part of the algorithm. That might be one direction for future work.
Okay. Hi. Two observations. First of all, I think you oversimplified classical optimization. It's been Pareto essentially ever since Pat Sellinger's original system R algorithm, because it was conditioned upon interesting orders, and later others, including myself, generalize that to any sort of physical property. So it's been Pareto for a while, although it's not sure how you would actually measure that.
So, of course, I simplified a lot. First of all, I didn't talk about interesting orders. I mean, you could imagine that in this algorithm, for instance, you have a Pareto frontier for each interesting order.
Or interesting partitions, or lots of different.
Right. And it's true that, I mean, I simplified, I mean, of course, I only have 12 minutes, so I somehow have to make a simplification when I discuss the state of the art. So yes, you might have had like intermediate stages between those two query optimization variants. And indeed, I mean, interesting orders also lead to that you have to keep several optimal plans for each of the subqueries.
That leads me to the second point, which is a suggestion, and that is for years and actually decades, Mohan has beaten me up because I didn't include locking the number of blocks in any plan that we would, in any cost model that we had, because I didn't know how to multiply a number of blocks and figure out how much time that actually resulted in. So I think you might consider that as one of the things in your Pareto optimization is the locking consequences of different plans. This would be a way to do it without having to have that metric.
I'm sorry, I think I didn't get the term that you mentioned, the what?
The number of blocks. The extent
right.
of the locking. Are you holding a record lock or
I see.
Lock?
Yes.
It makes a huge difference to the entire workload. And if that isn't included, it can have very significant consequences to the entire
So you
workload.
propose to add this as an cost metric? Yeah. Sure. I mean, this algorithm is, in each case, not specific to the cost metrics that I have shown in the experiments. If the cost metric is monotone, so if you improve subplans, so if improving subplans leads to an improvement of the entire plan, then it should work. So that might be the case for that. I would assume probably that is the case for this cost metric as well. And then you can use this algorithm in order to optimize with it as well.
I will ask one question as you're switching laptops.
Mm-hmm.
So what's the effect of the grid size?
So the grid size is actually something that we vary during the algorithm. I have not shown it in the simplified version, but we actually increase. So we increase the resolution, meaning that we decrease the size of the grid cells over time. The reasoning behind this is that probably at the beginning it doesn't make too much sense to use a very fine-grained grid because probably you don't know all the relevant subqueries yet. But then over time, once you can assume that you probably have a good sample of the relevant subqueries, then it makes sense to also refine the approximation for those subqueries. And this is what we are doing. I was going over those details.
Thanks. Okay, let's take a one again.
Thank you.